Okay, why don't we get going? Such a long class. Yes. All right. You have a question. I think it's a public question. Right? Is it a public question? No. Okay. Um, so the answer is I would see a doctor about that. No, I'm kidding. Um, uh, so uh, so in any case, what I'm just going to do this as open questions about projects. So this is kind of a discussion part of the class, and we just do open questions, and you see how much you can squeeze out of me, and then we go home. And let's not do this for too long because we kind of promised to run shorter today. Now I am thinking because as we get towards the midterm, you're going to be stopping wanting to learn anything new and wanting to have more review. So what I'm thinking of is like adding a number of extra office hours to just have open questions, and I might run those in slightly bigger rooms so that multiple people are in there. So that's one idea I have. Does that sound like a good idea to have more office hours? Will people come to office hours? Who would come to an office hour that's about review questions for the midterm? Yeah, you should say yes, right? Because there's no cost to say yes. I'm like not writing your names down. So I'm like guy in red, lady. Okay. So I'll do that. But also as a kind of a counterweight to that is we only have really one more thing I want to talk about, finishing the semaphore discussion and then talk about deadlocks just a little bit. We have plenty of time to do that. So instead of finishing that tomorrow, I think I will just not have class tomorrow. So we will have no class tomorrow, and we'll just have more office hours. Is this a good thing? And I'll do the office hours more and more next week, really, because I assume that next week will be the focal point. I might add a couple this week, but I'll add some more and more next week. So that will be our trade-off, and hopefully it'll be a good thing. But we also will have class next week where we'll do a little more material and then a bunch of review together. So now we're just doing open project questions. People have any? Yeah.
Do you see time benefits in zipping while writing? Does that make sense?
Yes. I'm just going to write questions down and then I'll answer them. By the way, like at the beginning of your life, did you ever think you would ask, what are the time benefits of zipping while writing? And that would make sense to this group of people here. Yes. Great. Yeah.
I kind of assume that we can load all files into no memory.
Yeah.
Do we get characters between files? Like, for instance, we put file into three lines that to backtrack to anything.
Any other questions? They seem to be zip oriented. Yes. I'm sorry. I can't see over there.
Is there an optimal size for buffers for whiteout?
Yeah. Any others? This is enough, probably. Okay, we'll go through these. If people have others, raise your hand. Otherwise, we can just stop. That would be okay too. And I'll just stick around if you don't quite feel like sharing. It's better to share though if you have a question. There's no bad questions. There are long questions, which maybe are bad. But so let's do these in shortest job first order. We've learned something here. So any characters excluded? Kind of, are you dealing with anything special? No, you should. You should not know anything about the characters that you're dealing with. All you're doing is when you're doing run length encoding of the bytes that are coming in, is you basically say, hey, is this byte equal to the last byte that I saw? If it is, it's part of the same run. Keep that run going. If it isn't, then it isn't. There should be no difference whether that's a /n, a new line character, or a tab, or a /0, which is just a bunch of zeros, 8 bits of zeros, or the letter R, ASCII code for R, or whatever. They're all the same. You should treat them all the same. Your code should not behave differently based on anything like that. You shouldn't write a line-oriented program to deal with this input. It should just be go byte by byte and just compare to the last byte and make runs out of that. Any questions about that? Okay, let's call that check. Let's talk about this one next, how to assume the files fit in memory or not. There could be a large input file. I don't think if you're doing this implementation in a reasonable way that you should have to worry about that. The reason is, for example, if you do mmap of a file, which we'll talk more about in a second in response to the fgetc question, if you mmap a file into memory, what that's doing is it's saying, here's a large file, and it's really easy to use, right? You just end up saying, pointer is equal to like mmap, and you give some flags here, and the man page even shows you the right code, or anything on the internet will show you how to use mmap. This pointer now logically points to the beginning of this file. But the OS is pretty smart about how it uses memory to access that file. So for example, a really naive mmap would take your address space, some part of your virtual address space. Remember those things are V address space or virtual address space. And what it would say, oh yeah, the file is right here in your address space, and that pointer, which we call this, it's really like pointing right there. And a naive implementation would just read all that data into memory, point all those virtual pages in your address space to those physical pages where it's just read in the file, and then you could access the file as if it's in memory, as part of your address space. But operating system implementers are smart, and they say that would be a silly implementation. What if you never access half those pages? I don't want to bring them all into memory. So the way mmap works is it faults in pages of the file lazily. So what that means is you can think of this file as having many pages, which are typically on systems these days are 4K in size. And what happens is when you use this pointer, when you dereference the first character, for example, this page will get faulted into memory. And then when you're kind of scanning through here, then this page, and then this page. And as you're going through the file, these pages, might get flushed out of memory. So unless you're doing something strange, like trying to read the whole file into memory, kind of touch everything, and then go back over it again repeatedly, you're not going to really have any memory issues. Even if you have a bunch of threads kind of processing through this chunks of this file together or at the same time, it shouldn't be kind of an issue. I don't think there's anything much to worry about. There would be a small case to worry about, which is like when I'm doing parallel zip. Maybe we'll talk a little bit about one other thing, which is just what's the pattern, kind of design pattern for the parallel zip. So maybe we'll talk about that a little bit. There's one issue there that I want to talk about that relates to memory. So I'll write that as a subsequent question. I guess I'll write it up here. So I'll just write it right here. pzip design pattern or something like that. So I'll talk about that too. Okay, so really quickly, let's do does that make sense to people about fitting in memory and kind of not worrying about that? Yeah. I think the work size, which I guess is a different question about the write buffer size. The size of work, let's talk about that in a second when we talk about the pzip design pattern, but certainly multiple pages, but I don't think it has to be one page. It's certainly something to consider. Okay, so let's do something, pattern. Let's talk about how to avoid fgetc. So that's really, again, the question of how to use mmap. That makes what mmap allows you to do is you get a pointer, and it's just, like a character pointer to the beginning of the file. And if we were doing the I don't know what's going on here, single threaded version, So just one thread. That makes it really easy. You just do a for loop of some kind for the size of the file, so you have to figure out how big the file is. And then you have a pointer when you want to access a character in the file. You just dereference that pointer, and then when down here somewhere you increment the pointer, and then you repeat, right? The files might be big, which means that make I, uh, you know, a long int. If you make it just an int, it's 32 bits. If the file's bigger than, a few gigabytes, you're going to get into trouble. And so just dereference the pointer is how you access the next character, and then increment it to move to the next character. Memory mapping is so cool, and we'll understand it better when we understand file systems. But it just allows that big file to look like it's just part of your address space, and you can just go through character by character in each one. So the first thing I would do if you haven't used mmap yet is figure out how to use mmap for the single-threaded version, and make sure your whatever you're doing works by just incrementing a pointer and going through the entire file. Any questions about that? Does that kind of make sense? And if you have code snippets that don't work, share them. We'll be happy to look at them. Okay, so that's that. Then there was I guess I'll answer these questions. So the time benefits of zipping while writing. So that's a bit of I guess first we'll talk about the pzip design pattern, and then we'll talk about that. And then finally, I guess there's this question of the optimal write buffer size. So why don't I do this one first, actually, and then I will do the pzip design pattern and go from there. So the question here is the optimal write buffer size, and I think this might be out of battery. Oh no, that's what it is. So probably not something you're going to end up worrying about a lot in this project, but at the end you have to essentially write something to standard out, and there's some when you're calling like the write system call, which you might do, let's say you're writing to a file descriptor of some kind, which could just be the standard out file descriptor, and some buffer and a size. This is a system call, and system calls have overhead, right? Because what are you doing? As you've seen already, that kind of code path is you're trapping into the OS, a bunch of registers get saved and stuff like that, and eventually the OS figures out, oh, this is a write system call, and then does the write, and then returns. So if you do this if this is very small, like let's say, and I've seen code like this, it's amazing, right? We had a grad student who was taking like a bioinformatics class, and he looked at the code that was apparently some code that's used all the time in bioinformatics, and he found that they were like doing these IOs and calling like writes and writing like 1 byte at a time to the OS over and over again. And he just changed that to write like 4K or 64K pages or 64K bytes at a time, and the program ran like 10 times faster. Because if you're just calling into something over and over again with like 1 byte at a time, it's going to go really slowly, right? So don't make this very small. How big should it be? I think you can determine this what we call empirically, right? Be empirical. So try, 4KB, try 64KB, something like that. Some chunk size that's not so tiny that you're just constantly calling into the OS to do something like a write, but it doesn't have to be that big. To essentially called amortizing the overhead. We want the overhead of calling into the kernel to be a very small percentage of the time that we spend doing things. So we just do enough work that that cost of trapping doesn't cost us that much. So that kind of is a rough answer. There's no great answer to that. It's not if we knew exactly what the overhead is, we could kind of calculate, if it costs us 100 microseconds to trap into the kernel, well, we better make sure that the kernel is spending 99 times that inside the kernel, because then we know 99% of the time it's actually doing work as opposed to spending all its time trapping in and out. So that's that piece. And what we have now is just let's talk a little bit about the pzip design pattern and then the benefits of zipping while writing, which are actually somewhat related. I'm going to switch back to blue. So logically here, you have, let's say we just had one file. We'll talk about multiple files in a second. And we split it up like this, and we gave each, the kind of natural thing to do is to create, you could just create, some threads and assign static work to each. And then wait for them to zip each piece. You could do this. And then kind of stitch together the final results. You could do this. And this would be a very results. This is kind of the simple approach. The problem, so does that approach generally make sense? You could say, okay, you take thread 1, take the first part of the file, so you give it an mmap pointer to this. You give another pointer to the second thread, and another pointer, and another pointer, and they're each given pointers to different parts of the file, and they each can kind of zip each part of the file independently. The problem with this static approach, static means we've decided a priori, no matter what rate the threads are running at or how fast the zipping within each thread took, we're deciding how much work they have. If one of the threads then takes a very long time because maybe it had a lot of runs to create instead of like one big run or something like that, then it's going to run much more slowly. So what's pretty natural, and I'm 100% sure if you talk to the TAs, from my understanding, that they would recommend is something that's a little bit more advanced. And it makes sense to me too. And the advanced thing is more of a dynamic approach to parallelism in general, which is what you're doing is you're dividing, let's say, the file, and it could be multiple files too, into some sort of chunk size. And we'll call this the chunk size. This is, again, something you determine empirically. Empirically means use measurements, like time your code in order to see if it goes faster or slower with different chunk sizes. So how big this is, who knows? But, it could be like a megabyte or something like this. Or it shouldn't be a byte. That's not a very interesting, if you're zipping a byte, it's not like a really good thing to be doing. You should be doing a chunk of code so each thread has some time to work on it. And so then thread 1 might get this one, thread 2 this one. Let's say pretend we just have 2 threads. And then when thread 1 is done with this one, it should then be given this one to work on. And then when thread 2 is done, maybe it'll work on this one. Maybe then thread 2 finishes this one first, so then thread 2 runs on this next chunk. That's much more dynamic. And if the chunks take different times to process, or if a thread runs more slowly, other threads can kind of take over and make progress. Now, the dynamic mode it means that there's like a main thread which needs to create like some descriptions of these works, right? Of the work that needs to be get done. So it needs to say like, oh, here's a pointer and the size, right? And maybe like, oh, that's chunk number 0 or something like that. Like, this is a description of work. It says, here's a pointer to the beginning of the region you need to zip. Here's how big it is. And that this is chunk 0, for example, or chunk 1. You create a bunch of descriptions of work, and then somehow there's a bunch of workers. And what they do is they get a work description and then do the work. And then they need to put the result somewhere that can be recovered later. So the main thread is creating work descriptions and then waiting for the workers to be done with all the work when they're all done, and then doing a little bit of work to stitch it together, then stitch together results. The workers just get work descriptions and do work, but maybe until they get some sort of signal that you're done. And once they're done, they, for example, just return, and then you can wait for them. This interaction between this main thread and workers, where have we seen that before? It's probably an OS class. It's probably recently. It's probably the producer-consumer queue. Yeah, that's not crazy, is it? Hey, the main thread is creating a bunch of work descriptions, which you're putting in a shared queue. consumers are just pulling those work descriptions off. They don't, poor workers, right? This is like their life. They go like take a ticket. What do I got to zip now? Then they go zip that thing. Then they go back there and they say, what do I got to do now? The main thread has a very good life, right? That's the boss. It's like, you do this. It just puts a bunch of work in there and the work gets done, right? And then eventually it probably puts some signal in there like, oh, the work is all done. So put enough, let's say there are 4 consumers, put 4 work is done tags in the producer consumer queue, and then when each consumer pulls it off, they return, and then you can wait for all the threads and kind of be done. So that's a pattern of interaction, and that's the only way the main thread should really interact with the consumers, or the workers in this case, which are consumers, is it gives them work. What the workers then do is, remember, they use that code that we already wrote together or looked at together to get the work description out of that shared queue. It doesn't have to be an integer. It can be like a pointer to a struct or something, right? They get that work description out of there, and then what they do is they work on it after releasing the lock and all that, and that's how you get the parallelism. And the zipping has to, of course, the overhead of getting the work should be much smaller than the overhead of doing the work, which is how you get to that, what size we should do of work. It should be big enough that we're amortizing the overhead. We're making ineffective or unimportant the overhead of getting the work, right? That should be a small amount of time. So that's kind of an advanced design pattern. You could, and this, of course, what's nice about this advanced design pattern is it works very well then across multiple files and things, because each pattern is just, some chunk of a file, and then if you move to the next file, the workers don't even have to know that. They're just given a pointer and how much of that file they should work on, how many contiguous bytes to work on, and then they just zip that. One last piece about this design pattern is, of course, this stitching together is a little bit tricky. The main thread creates all these consumers, gives them all work to do, and keeps giving them work until the work is exhausted, so all the chunks have been processed. The worker threads have to then produce that work, they produce the outcome like the zipped, ordered thing in some sort of global data structure that the main thread can then access, right? So you could imagine a lot of different ways of doing that. You could imagine, for example, the workers could each, there could be like an array, for example, like an output array. This would have one entry per chunk of whatever file or files we have. So, entry 0, 1, whatever. And then each one of those would be whatever came out of the individual zipping that happened. So it could be like a list or something like that of the zipped contents. So it might be something like, there are 3 A's followed by 4 B's followed by 16, \n's followed by, 2, whatever, R's. That could be one of the zipped outputs. And then what the main thread does is then just go through this and essentially kind of write it out. The only tricky part is what we already talked about way earlier in lecture. You remember that years ago, when you have to kind of stitch, if the last thing in one zipped output is the same as the first letter in the next zipped output, you have to combine those two. So that's a kind of a case where you just combine those and make a simpler, a more compact representation of that run. So in that case, like if there was an A that's the last character in this run, and this chunk and an A in the first character of that chunk, that should turn into 2A, not 2 individual 1As. So that's like the advanced design pattern of this project using a producer-consumer queue. I don't think it's too bad, but it has a bunch of details you have to work through, but then you'll have learned how to use such a thing. Yeah?
So, do we use that like output array with one entry per chunk? Do we have to worry about for really large files, like the size and like all the data values?
Yeah, you would have to worry about that in a real implementation. We're going to use, there's going to be a lot of compression, so in other words, this won't be too big. So you don't have to worry about that too much. Now that question there was this question about and the last kind of question was, do we have to worry about zipping while writing? And the reality is that doesn't really help very much, because you have to basically do all the zipping before you do much writing. You could do a little bit of overlap, like, yeah, I'm done with this first chunk and first two chunks, so I could see, maybe I could start writing those to disk. You could try overlapping that with the rest of the zipping that's going on. I don't think you're going to get a lot of benefit from that. You might get a tiny bit, though. It's a lot of work to get maybe little benefit. So always measure with timing, like how long chunks of you, like the zipping part is taking. That's going to be most of your code. Getting that efficient is going to be much more effective than worrying about that last bit of overlap. Yeah.
Wow, and nice solution is I created one of the workers for each chunk, and that system scheduler, we do scheduling, and we don't need to use producer and consumer models, so what's the better side?
Yeah, so the question is, if you didn't hear it, instead of using a producer-consumer and just a mild number of threads, what is being done in this solution here is, like I take the file, I just chop it up into, however many chunks, let's say 100, and then I just give each thread a static chunk of the work. Is that what you were saying? Yeah, you could do that static approach. That'll get you, I think, like a good chunk of credit. If we have a test where we've slowed down one of those threads and we have horrible ways of doing that, then what will happen then is that thread will run really slowly, and all the other threads will finish their work, and therefore you're not doing like any load balancing. You're not reacting to the fact that there might be differing amounts of work. So you'll probably get most of the credit, but you wouldn't get all the credit, assuming we do that testing in the devious way that we plan to. Yeah, it's life. It's hard. Life can be hard. Okay. Yes.
If you use this static approach and divide the work into so many pieces, so that the slow one will maybe use one for the CPU and the other one will use the other one, so that you can balance the work. So if you divide the work into smaller pieces, so that
Yeah. If you do a static division and one thread runs more slowly, it's not gonna run effectively, right?
but all the other work can be done really.
It doesn't matter if you do a static division of work. If one runs slowly, the others will finish, and the one won't. And that's it's some mild kind of problem. How big of a problem it is depends on how the circumstance. But there's no magic way around that. That's just going to run more slowly. Yeah.
It's not a good producer consumer, what's the ability for the first, like first 10,
Yeah.
file, and that just
Yeah.
never gonna finish, like, unappreciated.
Yeah, you're right that the producer-consumer queue doesn't solve that problem completely. Like if one is infinitely slow,
Yeah.
the only way we could deal with that is recognize that this actually happens in like in Google MapReduce clusters. They're using clusters to do this kind of parallel computing, and they give work to all the different machines, and then each one's doing an independent bit of work. And then what happens is one of the machines is like running so slowly it's never going to finish. So what they do is they recognize it and actually give that same work to somebody else, and then have them complete it. You don't have to do that here. So you're right, if something runs really, really, really slowly, you're not going to solve that problem. You're still going to be stuck waiting for that one thing. But if it just runs like twice as slow, you should be able to deal with that by giving work elsewhere. And again, the most advanced solution. Any other questions? All right, I feel like I've made this project worse for you all. You're welcome. That's a really interesting question. A question about variable chunk size. There could be. I wouldn't worry about it though. I think that if you somehow knew something like this chunk, bigger chunk, is going to cost kind of take the same amount of time to compute as this smaller chunk. Like you had some sampling of how many run lengths how many encodings, little runs were going to be inside of each chunk, then you could maybe do something intelligent and give like a bigger chunk with less work to do to one thread and a smaller chunk with more work to do in it to another, and they would kind of finish at the same time. But that's so sophisticated and so hard to get right. You're better off just kind of picking off my, horse sense on this or whatever, is that you just pick a fixed size and make that so that there's enough of those small chunks that each thread can kind of do many of them before you're done. Any last questions? Well, why don't we do this? We'll end now. I'll just stand up here. If you have any other questions, I'm happy to answer them. And remember, no class tomorrow. How exciting is that?
Can I pull up some of our code? Have you take a look?
Oh, it's like, yeah, sure.